All right, in this lecture we are going to connect the idea of geodesic deviation with just another analysis. You can't understand this too well. A couple lectures is certainly worthy of our time. If it was a regular course like at a university, you'd probably only do one class on it and then assign a lot of reading. We have the luxury of doing as many classes as we want, and so we're going to do another one. This one will be sourced from Meisner Thorne and Wheeler, by the way, so you can go to Meisner Thorne and Wheeler, chapter 11, and you'll see a lot of this material. Like I said, I don't invent anything here. I just choose the stuff that I like, that's taught me. And let's see if we can go back and remember a few of the key principles we covered last time. And one of those key principles is that our geodesic deviation we are going to treat as the second total derivative of the geodesic path, which I guess is S and T, as the second total derivative with respect to the parameter of along the geodesic. Remember, this is the parameter that connects adjacent geodesics, and this is the parameter along the geodesic. We can consider this to be the proper time, for example, along the geodesic. And that we came to identify with the second partial derivative in the direction, right? The second partial derivative in the direction of the geodesic twice of the connecting vector field, right? So this expression is what we mean by geodesic deviation. And we also remember it's not the straight deviation, because geodesics could be deviating in a linear way. It's the acceleration of this change. So if I connect 2 points of, say, tau equals 0, both of those are tau equals 0 along geodesic, say, n, and geodesic n plus delta n. You know, the curve that connects all of those geodesics goes through here, and if they're close enough, we can connect them with a little vector that we pretend lives in the underlying space. And then, of course, this vector field here is the v vector field, and this vector field here is the z vector field, just to remind ourselves of some of the definitions. And this curve here is gamma of, I guess we went with st, so it'd be n plus delta n tau, and this is gamma mu, and this is gamma mu of n tau, right? And so this expression here is how this guy actually accelerates as you consider movement down the fiducial geodesic, which is called n in this exposition. All right, so the Meisner Thorne and Wheeler approach to this is that we first look at, say, this stream of geodesics in space-time, and this is our parameter s. You know what? I better change this back to s because we used s in the last lecture, right? So it's s plus delta s, s plus delta s. Yeah, there we go. So it's first we'll just use s as our parameter, but we'll still use tau as our parameter along the geodesic. And then, like I said, the vector field u along the geodesic is these tangent vectors along the geodesic curve. Since I drew these curves relatively flat, then you know they're gonna kind of overlap the curve itself. And then the vector field that connects geodesics of like values of tau, say we started, that's tau equals 0, for example, and then say something like that, and then I connect each one with the curves that connect all of the like values of tau together. Oops. Something like that. And then the tangent vectors for those curves, those tangent vectors are z. I guess how would I do that? I need another color. Okay, so I went with magenta. So these magenta vectors are supposed to be the tangent vectors to these blue lines. I don't know why I did the blue dotted. They don't need to be dotted. They're just as important in this exposition as the geodesics themselves. Okay, so the blue obviously are lines of constant tau, and the geodesics are lines of constant s. And by this we have created a coordinate system. These lines, these vector fields here, this vector field, right, of the magenta vectors, which are, I guess I should write down, the magenta vectors are what we were calling the z vector field, and the green vectors, and the green vector fields we were calling v. So the geodesic tangents were v, and the connecting vector tangents are z, or the connecting vectors are z. Now, of course, when delta s is small, we can approximate these vectors as though they live in the space, and we can literally connect those 2 points with these connecting vectors. Likewise, we could connect these 2 points here, this point here and this point here, with the vector of tangency at that point, as long as everything is compressed to the infinitesimal. All right, so now with this idea, we know that along any of these geodesics, what is true is that the covariant derivative in the direction v of v equals 0. That's the definition of a geodesic. It has to do with the fact that when you parallel transport the tangency of a geodesic, that parallel transport ends up being the tangent of the curve at that point. So this geodesic curve has this very special property that if you parallel transport its tangent vector at any point to another point, the resulting parallel transported tangent vector equals the tangent vector at that point. So this is the definition of the geodesic. It's the geodesic equation as such, right? And I'll label it right there so you remember that. Now, Meisner Thorne and Wheeler likes to point out that this is actually a second order differential equation, because remember, this curve here is given by gamma mu of s and tau, and v equals the partial derivative of, well, I guess v mu is the partial derivative of gamma mu of s and tau by d tau. So this guy here is already a first derivative. This asks us to take the second derivative, right? Right, so by definition, this structure here is the vector down here. It's contracted into the covariant derivative of this vector here, and then with this upper index combines with this index to give you a vector, right? Notice it's in the coordinate basis, and here's the basis vector. So this guy, of course, can be expanded in using the definition of the covariant derivative as such, right? So we just took this symbolism and just replaced it by its definition. And then as a last step, I guess it's not really a last step, it's a second to last step, is I now take this guy and I substitute this, which is the derivative of the curve itself with tau here, and then this guy here is the derivative with respect to the coordinate alpha, which we've labeled gamma because, again, our curve is gamma of mu. And this is going to cancel with one of these, this derivative here will cancel with that, leaving us with a second derivative of tau in the denominator. Oops, I just realized, of course, you can immediately see something's wrong, right? Because this alpha contracts here, but if you look, this alpha doesn't contract with anything here. That I was a little too flippant. I should have written that delta must necessarily be an alpha. It has to go away, right? You can't have that delta there. So, I mean, a sigma. That sigma needs to be an alpha. And so you get, remember that, I switched those to alphas. Although this one doesn't look very good, alpha. And look, that's just the geodesic equation right there. That equaling 0. Remember, that's the geodesic equation, and it's an equation for the path. It's an equation for the geodesic in terms of the proper time. So if I solve that equation, it's a second-order differential equation for this line. Meisner Thorne and Wheeler makes a small paragraph reminding us that this looks like a first-order thing, but when you actually unpack it based on the definition of the tangency to a curve that is a geodesic, this equation is true, but once you flush it out, you end up with a second-order differential equation. Okay, so that point aside, let's move on. All right, the next step in this analysis is to consider that the geodesic equation of that curve is covariant derivative in the direction v of v equals 0. And in this case, that curve is evaluated at s, right? That curve is evaluated along s. So I have to choose a constant. That looks like a delta, doesn't it? A constant value of s. And it's going to be a function of tau along that curve. So the way to think about this is this covariant derivative in the direction v of v. This guy here is a vector. And it's actually a vector field, right? This is a vector field because remember we have this family of curves, s and t. And that family of curves generates a vector field. And that vector field we're calling v, right? It's these green vectors, whose formal definition is going to be partial gamma mu of s and t, partial tau, right? Partial tau. So, s is obviously held constant in that condition. So this object here is a vector field, and a vector field, in order to means there's a vector at every point in space-time, and in this case we're dealing with a two-dimensional space where one direction is parameterized by tau or by s and the other by tau. So this is here now the name of the vector, and these are the two arguments that identify the place in space with the vector. And we know that s and tau can form a coordinate system, and we know that because we've proven that vz equals 0, right? And we did in that lecture on holonomic coordinates, we showed that if two vector fields have a commutator equal to 0, then the curves that those two vector fields define that cover space-time, those curves can actually be the coordinate curves of a real coordinate system. And therefore, v and z can form a coordinate basis at every point if we switched to those curves. If we switch to those curves as the coordinate curves, then these guys would be the coordinate basis vectors. Anyway, the point is that this guy here is a vector field, and this vector field along this curve S, where S is held constant and tau moves, we're going to write down the that geodesic equation for that particular curve this way. That's what this evaluated at S means. Another way I guess I could have written it is the covariant derivative in the direction v of v. This is a vector field of S and tau, but what I do is I write down something like S equals constant tau. So it's now just the vector field along the curve with tau equals 0. Notice if tau is constant and we change S, these are not geodesics, right? These are not geodesics, as far as I know. And therefore this expression is not true, generally speaking. These I'm guaranteed it's true because I constructed them by definition. I asserted that they're just geodesics. So this is what I mean by this. Then I can do the same thing for the next curve. I can write the covariant derivative in the direction v of v evaluated at s plus delta s equals 0, because that is also a geodesic curve. It's just the one labeled by s plus delta s. Okay, and with that, I can write the difference between the two. And here we have it, the difference of this geodesic here minus the geodesic equation here. I'm actually subtracting the two geodesic equations. right? So I'm subtracting the two geodesic equations. In fact, if you went back here, it'd be like taking this guy and subtracting a whole nother one. But here I need to show explicitly that this is an equation for gamma beta of S, and another version would be for gamma beta of S plus delta S. So I guess I need to write, hold on, I guess I need to do S tau, and then this is delta S tau. They both share the same tau, by the way. So this difference, it's still going to equal 0. It's still going to equal 0 because both of these are geodesic, so they both satisfy the geodesic equation. So that equals 0 by hypothesis, and that equals 0 by hypothesis. So then I take this, but I still have this problem, right? This is at a different point in space than this. This guy is along this curve. This is a vector along this curve, and this is a vector along this curve. I can't really subtract them unless I parallel transport one to the other location, or if I parallel transport them both to the middle, maybe. I got to get them both parallel transported along these connecting curves. I got to parallel transport them to the same place. So when I write it this way, I'm implying that I've done some parallel transport where I've either brought this one to that location by parallel transporting it along the curve distance delta S, or I've parallel transported this one to up the curve by distance delta S. But if I do that, I find that difference and I subtract delta S after the parallel transport, I'm still going to get 0. But because I've done the parallel transport construction here, this derivative has to be understood the only way that makes any sense on a curved spacetime. This is a covariant derivative, obviously, and it's the covariant derivative along these curves S, whose vector field is Z. So this guy is going to equal the covariant derivative in the direction of Z of the covariant derivative in the direction V of V. And that, if I bring the 0 from here over here so you can see it, that equals 0. Okay, so now what somebody noticed is when you take this guy, you can think of it as part of a commutator, right? You can think of it as part of this commutator, V of the vector V, right? So that commutator would be partial, I keep saying partial, the covariant derivative in the direction Z of the covariant derivative in the direction V of V minus the covariant derivative in the direction V of the covariant derivative in the direction Z of V, which I suppose would be a little bit easier to write like that. So this piece here is actually this guy right here. So if I was interested in this guy right here, right, what I would say is that this guy here equals this, well, it equals this minus the commutator. Let me write that down. So this is the expression that we're looking for, right? The covariant derivative in the direction V of the covariant derivative in the direction Z plus this commutator acting on V equals 0. This expression here is equivalent to that. It's algebraically equivalent, right? It's not a very clever, well, it's clever, I suppose, but it's not particularly insightful, right? This, by definition, is this thing, right? And this plus this, well, that cancels with that, leaving this, which is all that that is. So this expression can be written this way. All right. So the next insight is to show that this operating on V is actually the geodesic deviation that we seek. And we've already actually done that demonstration in the previous lecture. And I'll just do it again because you can't do these things too many times. So let me just move this up like that. So the way this worked was we know that the commutator of v and z by construction equals 0. We demonstrated that. But we know that that equals the Lie derivative in the direction v of z. And we showed already that any expression where we substitute in for this Lie derivative, we can replace with covariant derivatives, right? So we know normally that that would be we know that it would normally equal this thing here. And now we can replace these with covariant derivatives because, as we showed in the last lecture, we can always do that when the space has zero torsion. And therefore, this is going to equal v alpha z beta double bar alpha minus z alpha v beta double bar alpha, which is basically covariant derivative in the direction v of z minus the covariant derivative in the direction z of v. And we know that equals 0, so we know that the covariant derivative in the direction v of z equals the covariant derivative in the direction z of v. Phew, okay. And I showed that last time too. So now we are going to look at this guy again, and we see we have the covariant derivative in the direction z of v, which is this guy, and I'm going to replace it with the covariant derivative in the direction v of z right there. So if I do that, let's see, I'm going to squeeze it in there, and I end up with this expression, this nice magenta expression, and this guy now equals 0. And so I've done all that to get this guy out front, right? That is the geodesic deviation. We showed that earlier. Right back here in the beginning, this is this geodesic deviation. This is what we're trying to solve for. We want to understand the geodesic deviation because we think, remember, we think in a flat space-time, there should be no geodesic deviation. The geodesics should not accelerate away from each other. But in a curved space-time, this is not going to be 0. So that is the geodesic deviation. So now we know that the geodesic deviation, which represents an acceleration, right? That's an acceleration, is basically equal to the opposite of this commutator. And that's a big deal. We write that down separately, and we're going to consider just this. So we're left with interpreting this expression. And this is an acceleration, right? We want to call that d squared gamma. Remember, gamma is a function of s and t. D tau squared, s and tau. So that's an acceleration. You can imagine putting a little mass here, right? Maybe a mass. Then this guy has to be an acceleration too. So if we understood that as a force per unit mass, and we multiply by mass, it would be a force. So this would become a force plus a force equals 0. So the way we want to think of it is this is an acceleration. This is an acceleration, which we know by the way we've constructed it. This has to be an acceleration due to just the nature of the space-time and gravity. You can kind of think of this as the tidal forces that induces this acceleration on the motion. Now, that's not what's going on in our GR view. In our general relativistic view, we have things moving along geodesics in a curved space-time. But what this says is that two geodesics, you'll see this acceleration, which will kind of appear to you like there's some sort of force out there if you impose sort of a Newtonian view on it. And if you did, you would interpret this commutator as being the source of that force. And in Meisner, Thorne, and Wheeler, you actually see them creating a direct analogy between this and the Newtonian picture in box 11.4. It's a great box. I'm not going to go through it. You can only steal so much from one book, right? But in box 11.4, they literally pair this up with the Newtonian expression that shows the acceleration, and this would ultimately be the force due to gravity, right? This is the force due to gravity right here in their analysis. But something should jump out at you when you see this, because we've already derived an expression for this in the last section. Let me write that down. I mean, the last lecture, and it doesn't end up being this. In other words, our expression in the last lecture for this geodesic deviation is not equal to this. So what gives? And I'm going to tell you what I'm going to tell you. What gives is that this, the foreshadowing hint is, this guy can be directly connected to the Riemann curvature tensor. But this is not the Riemann curvature tensor. So, but this is still a true equation for the construction we made. So now the question is, we are going to get at how we defined that curvature object. Remember, we had this curvature object that took two vectors, A and B, right, and gave us a result of another vector as a result. And I defined that by sort of fiat. I told it to you and accepted it from the very beginning. Now we're doing an analysis that's going to reveal why we chose the definition we did, because you'll see that that definition is motivated by this analysis. The first point is this is true. This is true, but this is not the Riemann curvature tensor. Okay, so here's what we're faced with. We're looking at the equation we just derived, right? And then we're looking at what we know from previous lectures, which really is all, you got to remember, this is all based on the fact that I defined something called RVZ, right? Which was defined this way. I guess RVZ acting on V was defined this way. And this is the thing that I've never fully explained where it comes from and why. So now it's the time to kind of blend all this together, right? We understand what this is from our construction. We built this from first principles. We also built this from we didn't build this from first principles because we were given this definition of the curvature, of that curvature vector form. So what do we do to make this right? Well, the first thing I'm going to do is I'm going to interchange V and Z here. That interchange of V and Z is just to keep the notation consistent, because when we derived this, I used a process that landed with VVZ, and it's a little more convenient to land with ZV. So what happens when I flip those two? Well, V flips with Z, Z flips with B. That's like taking this guy and putting it here, and this guy putting it here. So the sign of this part flips, and then this flips in sign, so that sign flips. So basically the sign of the whole thing just flips. So it's anti-symmetric in those two, in these two slots. And so there you have this. Now this term goes to 0 as before because of the this is a geodesic, so that's the geodesic equation built right in there. We know that that equals 0. And this goes to 0 as before because the commutator of Z and V is 0, as we've demonstrated several times. So we've got that going away and that going away. And all that's left is this guy here, which we've already shown is the same as, where did we show that, right? Partial V, the covariant derivative in the direction V of Z is the covariant derivative in the direction Z of V. So the covariant derivative in the direction Z of V is the covariant derivative in the direction V of Z. So we end up with comma minus covariant derivative in the direction V, covariant derivative in the direction V of Z. And you can see that had we done the same thing up here, we would have lost that term, and we would have been left with this term. We would have replaced this with that, And the only difference would have been this minus sign, which reflects the fact that it's anti-symmetric in these last two indices. Another way to say that is, right, if you wrote this in component form, alpha, beta, gamma, delta, that equals minus r alpha, beta, delta, gamma, right? This is the coordinate version of this anti-symmetry that's reflected by the introduction of that minus sign. So we're faced with a bit of a problem. In our first lecture, or in the lecture we just completed, this lecture, this is what we have shown, that the geodesic deviation is equal to this expression right here, this commutator of these covariant derivatives in these directions on V. And of course we constructed this very carefully and we've come up with this answer. But in our last lecture we showed that this was true, that the geodesic deviation was equal to this Riemann tensor, and that Riemann tensor was defined through something we called the curvature, which ultimately was this same commutator, right? The same commutator as this, but we also have this extra piece right here that involves the, I'm missing a bar here, the covariant derivative of the commutator of V and Z. Now we know that by construction, this part went to 0, so it really didn't affect things. So ultimately, when this part goes to 0, you get this. But then why include it in the first place, right? We've derived this expression from first principles. In the last lecture, I kind of gave you this structure here and called that the curvature. So now we got to sort of resolve how that works and why. So to do that, we're going to have a close look at this general construction. The covariant derivative in the direction A, the covariant derivative in the direction V, acting on a vector C, right? So this is literally going to literally equal this thing right here. So what we want to do is I want to study how this structure here depends on variations of C. So you got to imagine a vector field C. So let's go to our point. It's the point P, and at that point P we have a vector, part of the vector field. And then at other points, you know, the vector field has its values at all these other points, right, including adjacent points. You can imagine this being the geodesics, right? This is the vector field attached to, say, our fiducial geodesic. Let's see, what would it have to look like? To look like that. And then this nearby geodesic would be up here, perhaps. But everywhere in space-time, you know, every point has an associated member of the vector field C. So C is a vector field on the space-time. So I now want to imagine taking C and multiplying it by an arbitrary function on space-time, right? So what we're basically doing is, I guess, stretching or shrinking C at every point by this factor f. So say I went to this point here, which maybe we call that point r. I take the value of f of r and I multiply it by the value of c of r. Now c of r is a vector, but f of r is a scalar, and I can multiply a vector by a scalar. So I basically am shrinking or expanding all of these vectors in a very arbitrary way, because I can do this with any function f. I'm only going to establish one criteria for this function. I want it so that f at p equals 1. So the value of f at this point here, at that point p, is 1, and therefore c, so f of p, c, f of p times c of p, let's see, the c's are looking like parentheses now, equals c of p, right? That's what I want. So essentially we've arbitrarily sort of scaled every vector in the vector field except for the one at p. I suppose there's some other point maybe in this vector field where f of x also equals 1. It doesn't matter, but it does matter that it equals 1 at p. So with that in mind, I have a new vector field, right? I have a new vector field called f of c. This, by the way, is demonstrated in Meisner Thorne and Wheeler, and it's as an exercise. I guess it's not really demonstrated. It's really an exercise. So what if I run this expression here with f of c instead of c? Let's see what happens. So this guy here is a differential operator, so it's going to follow the sort of the Lorentz. It's going to follow the Leibniz rule, and so it's going to act here on f. Multiply that by c, and then its f is going to factor with the differential operator acting on c. Now if I look at this result and I say, okay, so what is the value of this object here? What is the value of that at the point P? Well, at the point P, we would expect that, well, look, f equals 1, right? So we might think, oh, okay, well, that should be equal to, this guy, well, at the point P, it should be equal to this differential operator times c, we might think. But if we look a little more carefully, we realize we can't put f equals 1 too quickly, because this is taking a derivative of a function. So we put f equals to 1, okay, so this guy goes away, right? That would end up being sort of equal to 1, which leaves us with this commutator on c. But setting this guy equals to 1, that's a little different now, because it's actually it's not f, it's this differential operator acting on f, and the value of that object is going to depend on the derivative of f, not on f itself. So the result of this commutator on a vector field that varies from c in the way we've constructed f is going to involve f, right? We can't get away from the fact that f is going to affect the answer. And the reason that that's a problem goes back to how we understand geodesic deviation. It shouldn't matter if I take a different vector field, right? If I switch this vector field up a little bit, or if I just change the rate that we go down this vector, this particular geodesic line, then I'm changing v along this geodesic, or along all the geodesics, and even maybe along this geodesic, but not at the point P. But the acceleration of the geodesic shouldn't depend on any of that. It shouldn't matter if I choose a geodesic that goes like this. But that's equivalent to introducing this arbitrary function f on the vector field v. So if this alone was the definition, oh, wait a minute, let me put it this way. If this here was the definition of the curvature tensor, you would notice the problem we would have right away is that this object here actually depends on the derivative of, it actually probes the space around the point P, because it would depend on a derivative scaling of v if we multiplied by a function f. So it's not really going to work because of that inclusion, because of that fact that this term here appears. Now let's try the same exercise with our actual definition of the Riemann tensor. That is, let's evaluate this thing with a variant on C that varies in the same way, with the same rule for f. What do we get in that case? Well, obviously, this is the same as this, so we immediately get these two terms here. Let me get rid of this blue. But we also get this piece right here. Right? This piece is derived from this section right here, again, using the Leibniz rule. So now if we look at this, we'll realize that this part here And this part here, when we are at the point P, right, those two will, the f's will go away, and you'll end up with what you would have gotten had you had no f here to begin with, right? If there was no f here, if that f was gone, let's see, if this f was gone and this f was gone, you would have ended up with this differential operator on C and this differential operator on C. And that's what this is here and this is here at P, right, when f equals 1. So, so these two terms alone at the point P give you the same answer with are not dependent on this variation of f. But what about these two terms, right? These two terms clearly are differential operators acting on f. But the fact is, it turns out these two are the same. And the reasoning is as follows. To see the reasoning is actually nice and easy. This is a good example of jumping into the coordinate basis and writing this out in terms of writing this and this out in terms of index notation. And we'll see that they are the same. So first, this first term here, this guy, right? That commutator is going to be this structure in index notation, right? You can end up with a covariant derivative of B in the direction of A, so that's going to be A acting on B, and then covariant derivative in the direction of B acting on A, and you'll end up with the covariant derivative of F as part of that whole thing in the direction of A or B both. So this is the index version of that. I think we've done that before. And the second term, that's this guy right here, I'm going to blow up that commutator. Now that commutator looks very much like this one, but it's only got single derivatives, or single bar derivatives, which are regular partial derivatives, right? Not covariant derivatives like those, regular partial derivatives. And this is in the subscript of the del operator, but f still is still the covariant derivative in respect to alpha. But we know by our rules of how these derivatives are managed, these covariant derivatives managed, this here is basically the covariant derivative in the direction of this vector acting on f. Actually, let me wait a minute. That's actually not exactly the right notation, right? Because what I've got here, look what I have here. This is the covariant derivative acting on f, but I have f already with an index on it, so I'm getting a little ahead of myself. It should just be this. This guy here is a vector, right? And this is the components of the vector. In fact, okay, let me actually do this even better. If I'm going to go in full component notation, I've got to then say mu, and then this whole thing, I got to give it its basis vector, partial alpha, right? That's the basis vector in the coordinate basis. And this whole object acts on the function f, right? So now I can take this guy here, and I can say this is the covariant derivative in this direction, in the direction of this vector, acting on f. And now I rewrite that. I'm going to move it to a different screen here. So I'm going to rewrite this guy. This expression, this expression right here, that's not going to work. It happens to work in this construction we made because this commutator here goes to 0. But in order for our tensor to only depend on the values that you give it at a given point. Remember, because this is a tensor, it's supposed to be a function of a point in space-time only. It's not supposed to have to reach out and understand what's going on in the nearby vector fields, or the nearby portions of these vector fields. So in order for that to work, you really need to add this little correction piece. And that little correction piece makes all the difference in the world. And it reduces to what we want in the particular construction we made, where V and Z are equal to, the commutator V and Z is going to be 0. Now you'll also be able to realize, well, okay, so this is also true that this is if you go back to our round trip analysis, this is the closure of a quadrilateral where V and Z are the vector fields that give the displacement of the sides. So this is another way of saying that we're going to drag the connecting vector Z around this quadrilateral. I'm sorry. We're going to drag, this vector V, this tangent vector V, around some quadrilateral involving V itself and this connecting vector V, and we're going to close that quadrilateral with this part. So we're going to drag it all the way around a polygon, and in the event that V and Z commute, well, then this term goes away because the polygon already closed. But anyway, that is our motivation for this definition of R we gave in the previous lecture. So the idea is that it's supposed to all tie together. For a deeper look at this, for a shallower look at this, I suppose Meisner Thorne and Wheeler, page 276. They basically ask you to do what we just did here as an exercise. And I guess that's sort of what we did. We sort of did this as an exercise, showing this fact here. Whoops. Not that one. Where did we do it? We did it here. Yeah, showing all of this was an exercise. So in summary, on our past 2 lectures, we've been able to show that the geodesic deviation is actually equal to the Riemann tensor applied to these tangent vectors and connecting vectors. And we've motivated now the definition of the Riemann tensor to be this, based on this round trip idea, and also based on the fact that we need to sort of eliminate this gradient effect from calculating this guy here. And this turns out to be the best answer for this problem. It's basically the only way to make this object a true tensor that really only depends on the values of the vectors fields at a single point. Because remember, a tensor this is a field, right? It's a tensor field. So R is actually a function on space-time. But all I should have to do is probe the value of the point in space-time to make it work. It has to be linear, right? To be a tensor, it has to be linear in all of these terms. In other words, you have to be able to write R of, if omega is the one form, let's see, little a, little b times c, little c times a, and little abcd times b, right? That had better equal a, b, c, d times r of omega, c, a, and b. Right? It's got to be linear. You've got to be able to add it together. It's essentially a vector space, right? Its tensor product space is a vector space. So this is a 1-3 tensor. So it really can't, but it's defined in terms of these derivatives, which is kind of amazing. But we just shown that in this form, it actually is a tensor because it doesn't depend on those derivatives. It looks like it depends on derivatives. But in the end, it only depends on the value of C, A, and B at the point that you're actually evaluating R. Meaning if you change C away from, say, C away from the point you're evaluating this tensor, despite the fact that all these derivatives appear here, it still doesn't matter. It all cancels out. So that's why this is an important term. So this is defined as the only way to make the curvature an actual tensor object. Okay, so now we've covered geodesic deviation, we've covered this round trip analysis. So we've now understand the curvature. So I presume at this point you understand R, alpha, beta, gamma, delta. That is the Riemann tensor in index notation. And of course that's going to be in our basis, in our coordinate basis, right, we would write that down as partial alpha tensor product dx beta tensor product dx gamma tensor product dx delta, right? And this guy embodies all of the notions of curvature as understood by these ideas of taking a vector and moving it around, doing a little round trip and getting the mismatch, or by looking at adjacent geodesics and noting the acceleration of one geodesic from another, which is really essentially our tidal force analysis. And we know that this guy was defined through the connection, which is defined through the metric. So if the metric gives us the connection, gives us the Riemann tensor. Yes, there is an expression for the Riemann tensor directly in terms of the metric. It's going to end up being in terms of second derivatives of the metric, g mu nu. And you can check that for yourself. You'll calculate this and you'll see this depends on first derivatives of g, and then you'll see that this depends on first derivatives of the connection, therefore this depends on second derivatives of g. So it'll depend on second derivatives here. Okay, so now we'll move on to other subjects. We're still working towards, in this we're working on solutions of the Einstein equation. So next we'll move on understanding, say, the Ricci tensor. All right, talk to you next time.